line 22, 7b97z69a, Debye-Scherrer rings trapped ions scattering electron beams, 5G Wow Seti. There's the alien radio signal. There's the data there. And this is trapped diffracted ions, electron laser beams for UFO space communications, line 22, Seti data, parts A and B. October 4, 2013. Today's November 10th. Previous video was line 22, 7b97z68 nanoparticles, femtosecond laser pulse diffraction lattice. And I just realized there was a formula in there. And for some reason, I don't have the word formula here. Okay, there you go. I can't type. Okay, keyword, diffraction from trapped ions. Quotes and diagrams from a blog. So here's a diagram of some scattered electrons. It says 10 to the power 3 E/E sec. Nuts in oven, Faraday cup, E-beam, RF trap, ionization gun, and microchannel plate. Okay. Figure 1. The overall experimental concept for obtaining diffraction patterns from trapped cluster ions is shown. Cluster ions can be stored in an RF Paul trap by in-situ ionization of an effusive beam emitted by oven. Trapped ions are then exposed to a high-energy electron beam to obtain a diffraction pattern with adequate SN to derive structural information. As a result of the orientational and spatial disorder of the trapped cluster ions, the diffraction pattern will be in the form of Debye-Scherrer rings, similar to powder diffraction. The primary issue is the small number 10 to the 2, 10 to the 5, and density 10⁶ to 10⁸ cm⁻³ of trapped cluster ions, which leads to a low rate of elastic scattering relative to the incident electron beam. In this situation, the challenge is to minimize the electron background scattering within the confined trap volume and the backscattering of high-energy electrons from the Faraday cup. And that's from www.genetical.com. Electron scattering in molecules. This is a gas phase. Electron scattering in molecules is composed of an elastic scattering from individual atoms. I don't think you can see that too well. It's kind of small. Let's see if we can make it a little bit bigger. It just goes blurry, so that ain't gonna work. Okay, so the interference, B is the interference of waves scattered from atoms separated by distances characteristic of the molecular structure, and C, inelastic scattering characteristic of the molecular electron energy states. The orientationally averaged electric contributions are expressed above in terms of the atomic scattering amplitudes of Fij. Oh, no, F. Yeah. And it's got F with a little ij down to the right, to the bottom of it. The atomic separations are in the same little ij, and the vibrational mean amplitudes of I and little ij. I don't know if it's I or L. The total elastic scattering intensity distribution is shown on the left as a function of S, and the separate contributions of the atomic and molecular scanners are displayed on the right. So it shows it on the left and then on the right there. And it's from www.genetical.com. So here's a beam data sequence, diffraction signal, ionization guns, E-beam, and a C60 oven. And then there's the background showing the pictures there. Diffraction data was obtained first from a neutral beam of C60 emitted by the oven source shown in figure 2 as it passed through the trap in the absence of RF voltage. In the beam data sequence, the diffraction signal is obtained for a period of time determined by the CCD. Pixel saturation and then electron background signal is obtained under identical conditions but with the C60 oven shutter closed. This data sequence is repeated over a total experimental runtime of a little squiggly line 2.5H at an E-beam current of 50 Na and an oven temperature of squiggly line 800K. Using the C60 vapor pressure, the number of molecules in the volume defined by the intersection of the molecular and electron beams is estimated to be squiggly line 5 times 10 to the power 5. And again, that's from the blog www.genetical.com. Keywords and formulas, trap, RF fields, effects continues in the next video. Thank you for watching.